Good afternoon. I'm a little behind. Doing okay.
All right.
I mean, not a lot. I just made it.
Okay. We're all set? Okay. Okay. Well, let's have a go at it. So, I guess Monday we were talking about mass spectrometry, giving you an idea what mass spectrometry is, kind of how it works. And now we're starting to talk about how do we interface mass spectrometry with other instruments. Because when there's something elutes off a gas chromatograph, you really don't know what it is. You don't have much to go on in terms of identification. The same is true of liquid chromatography. And so it really makes a great deal of sense to be interfacing mass spectrometry with some kind of a separation technique. It's very, very seldom we have a pure system, absolutely pure compound we want to analyze. And so that's what we're going to spend a few minutes talking about now. We'll also get into some applications of mass spectrometry. And I think I mentioned also to you earlier that one of the problems is these things aren't run under very high vacuum. The better the vacuum, the better they run, the better the data you get. And so when we start interfacing them with a gas chromatograph, we've got a mobile phase of gas. Pump the gas into the mass spectrometer. And okay, we've got to get rid of that gas that we're pumping in. We've got to try and maintain our vacuum. The same is true of liquid chromatography. And so we look at what kind of interface. How do we get an interface in here we can live with? And if we go back in history a while, gas chromatography or gas chromatography used to use fairly large columns, a 1/4 inch in diameter. Of course, what I was talking about for today's gas chromatography uses millimeter, 0.2 millimeter columns. So today we have tiny columns, which means we have small gas flows. So we used to have very complicated systems of getting so much darn gas out of there to get it into the mass spectrometer. Now our flow is sufficiently small that we can actually make a direct interface. We can tolerate, a mill a minute gas going in, but we can't tolerate 10 mils per minute or 20 that we used to do. So actually, the improvement in gas chromatography made mass spectrometry easier. And so end of the column simply goes right into the ionization source of the mass spectrometer. We've got our filament, rubidium filament here, getting off electrons, high energy, bombard them, break them into fragments, and on their merry way they go. And so we do have to have good vacuum systems for that. Even a mill per minute turns into something like 10 to the 6 mils when it's drawn under a vacuum. So 10 to the 6 mils of gas per minute coming in, yeah. It still requires a good pumping system, so we've always got a dual pumping system in these mass spectrometers. There's typically some kind of a rotary pump. We call it a roughing pump usually, or a 4 pump. It may bring the vacuum down 10 to the 2, or, well, 10 to the -2, 10 to the -4. It should be -4, or 10 to the -4 torr. But then we need to get down preferably 10 to the -6 over here. So there is then a turbomolecular or a diffusion pump that goes in the heads and brings us down the rest of the way. So it's a 2 pumping system. One that pumps out the bulk, and the other one that's kind of a finishing pump. This is a turbo pump. It's rather interesting that you actually do have a system where there's a rotary turbine in there. This turbine is spinning and moving gas out of the system. And this spins about 55,000 revolutions per minute, 24 hours a day for years. It absolutely amazes you, what they must have for bearings and how they keep something like that running. That's the most common. They say short lifetime, 1 to 2 years. Probably 5 years is more reasonable. They will run on that basis, 55,000 RPM for that time period. Then, yep, they need to be rebuilt, new bearings in them. This is what I mentioned about, we do have to pump out 10 to the -6 mils per minute. 1 mil goes in, but under vacuum expands to 10 to the 6 mils. So we do need really good vacuum pumps. So this is our system. If you go down in the lab, we've got several of these sitting in the laboratory. Here's our column. This shows an old column, a packed column, a big column. This today is, of course, 30 meters, a very small column. Goes in, here's our ion source, here's our separation of the ions, and here's our detector. And of course, printout on the end. I also showed you this one. When you see one peak, whether it's from a gas chromatograph or from it's a liquid chromatograph, you don't know that that's one compound. It may look like a really beautiful peak. This orange one up here is what you would simply see if we don't have a mass spectrometer on the end. We see a nice peak. And if we start looking closer into this example, this peak is actually made up of two other components. So we would have a bit of a problem identifying these and quantifying these if the mass spectrometer weren't smart enough to say, you notice these two peaks are just a little difference in time, a little bit of offset. And so the mass spectrometer says, okay, what masses are moving along at this rate and which masses are moving along at this rate? And so it puts them together. Everything that's moving a little bit faster, a little earlier, that must be one compound. The other one that's moving a little slower, that must be another one. And then it goes through and does its identification work. But it's really a nice technique for that. And in fact, we can quantify compounds on this basis. We don't even have to separate them. I said we don't need to go baseline separation, gas chromatography. Well, I can separate that into two peaks. That looks like one, doesn't it? And the mass spectrometer was separated into two, measure them both properly. So, again, just a marriage made in heaven, literally, getting gas chromatography and mass spectrometry together. LC, I have to concede, yes, is the hottest area. That's a concession to your instructor, who loves liquid chromatography. And it's becoming into its own. It's really well established in the food industry. There's been so much advances in liquid chromatography too, that it truly is moving more and more into the labs everywhere. Cost has come down, so cost is reasonable, and capabilities have been improved. And now, again, putting liquid chromatography together with mass spectrometry, it gives it a great deal more power. The carrier flow is one of our problems, your mobile phase. When I talk about gas chromatography, I'm talking about 1 mil per minute of gas flow. Now, in liquid chromatography, what flows do you run through the? But that's that's a liquid, which then changes into a gas, it goes into a vacuum. And so your volume is much greater that you have to pump out or deal with in a liquid chromatograph than in a gas chromatograph. And so that really dictates some other types of inlet systems, ways to manage, again, that liquid, changing gas and expanding. And so we find techniques called atmospheric pressure chemical ionization, electrospray, thermospray, particle beam interfaces. You get a lot of innovation, a lot of processes that people can use to try and get rid of that mobile phase. And this is electrospray. It's one of the more common types of interfaces. So what we would have is we would have your liquid chromatograph over here. You'd have your effluent from the liquid chromatograph coming into the system here. You'd have your inert gas coming across here. There's 4,000 volts on this internal, let's say, inlet system. We'll look down here. And what happens is this sprays, and it sprays droplets, and those droplets take on a charge. They take on a charge from a big 4,000 volt potential here. And the solvent tends to evaporate in this region. And so it ends up with the solvent evaporating. And it leaves a charge on your particles. So your analyte is in here in this mixture. And like I say, the solvent tends to evaporate, leaving a charge. And that's what we want. We want a charge that gets drawn then into the mass spectrometer. So your solvent tends to be carried out of this system, and your analytes end up entering the system. So it's a very, very common technique. This is a different one, a different inlet, one that I happen to like and have used a fair amount. In my case, there isn't any kind of an LC attached to it, but there certainly can be. And so this is at least under atmospheric pressure, which is kind of interesting, but it's the same type of the system. where you will draw, in this case, gas in potentially. And here you have a needle that carries maybe 5,000 volt charge on it. And so that gives you a charge to anything that comes out. So your analyte will come out here, be carried through the system, takes on a charge from this electrical charge here, gets drawn off and into the mass spectrometer. In our case, what we use it for is we want to analyze flavor compounds in a person's breath. And so we'll actually take you, set you in front of the mass spectrometer, put the little tube up your nose very gently, and we will monitor what you breathe. You'll take a food into your mouth, you chew it up, you swallow it, and the mass spectrometer will sample your exhaled breath. And so you can monitor the flavor compounds in your breath from the food you just ate. Really fascinating technique. MS presentations. I think I already mentioned somewhat of this, where you will always monitor a total number of ions that are formed from the effluent of the gas chromatograph or the mass spectrometer. But you're always sampling this by the mass spectrometer. You're taking full scans that you can look at. You can use these for identifying what's the compound. Does that compound change over the time, for example? Is it one pure compound, and so on. So it's really a very, very strong system, a very, very useful system. When we want to quantify something, again, in our particular field, but it can be any other field as well, it's really nice to have a system like, based on a stable isotope. And I'll show you how a stable isotope is useful. It's your internal standard, essentially. And like I say, I'll give you an example of that coming up in a minute. So you'll take your sample, you'll spike it with an isotope of what you want to measure. So your sample has a known amount of this isotope and an unknown amount of the compound you want to measure. And then you can do your mass spectrometry, and you will monitor the mass of the internal standard, your isotope, and the mass of your unknown. And you can then do your quantification. And I show this to you as an example. What we're doing, 5-fluorouracil in blood plasma, hardly food science, but it's exactly the same thing in food science. So I want to measure this dimethyl 5-fluorouracil. And if you run this on a gas or liquid chromatograph, you would of course get a trace from it, but we want to make the mass spectrometer very specific. This has a very strong fragment. As we break down the effluent from the LC, a very, very major fragment is mass 158. And not a lot of things are going to have 158. So it's very specific. It's going to monitor primarily this one compound. And so if we just monitor mass 158 and nothing else, this is what we see for the 5-fluorouracil. If we want to make an internal standard, what we do is we synthesize this with a nitrogen that is 1 mass bigger. And then we add it to our sample. We do all of our isolation, analysis, monitoring, except we monitor, well, we got 2 nitrogens in here, right? So there's 2 nitrogens. So this is mass 158. We monitor only mass 160. So what better reference, what better internal standard than the compound itself? And our mass spectrometer is able to, we won't separate these. We won't separate by gas chromatography and mass spectrometry. They will co-elute, but the system's just set up. It's only going to monitor these 2 masses. And so if we know this corresponds to a certain concentration, we can just simply proportion. If this peak's 10 times bigger than this, there's 10 times more than this. So it's really a beautiful internal standard. You know, when you choose internal standards for a method, you always choose something that's closely related to the compounds you want to measure. It's just good practice, so they behave like the compounds you want to analyze. And there's no better standard than the compound itself, just 2 mass units bigger. Purity of GC peaks, you can never be certain, like I say, that a peak that comes off a GC or an MS is a pure compound. And again, that's where mass spectrometry comes in nicely. Let's check it. We get a mass spectrometry, or mass chromatogram, I'll call it that, of a peak. You can tell if it's one compound or two, and you can tell what compound it is. It just really is very, very, very comfortable for identification. We really have other ways of doing separations, quantifications of compounds that don't separate. And this is another methodology. It's called MS, where you do mass spectrometry, and then you take that some peak, and I'll show you, in that spectrum, and then we'll bombard it again to get a mass spectrum of a part of the mass spectrum. That will make sense, hopefully, if it didn't. And so, again, let me take a look and see. So, okay, here's a triple quad MS. Basically, we can have either a GC or an LC, putting our sample in here, doing our bombarding, doing our separation, and we'll finish our separation here, then we'll actually bombard a fragment of that again. What we want to make sure is that when we get a spectrum, the spectrum may be fairly similar, but they could be made up of different masses. And so this permits you to look at every fragment and see that those fragments are the same throughout the system. If that doesn't make sense, I probably won't put more effort into it, but it's absolutely a great way to, again, make sure the compounds are the same, or if they're not the same, that you can actually separate them. So you may have the same fragments, but you look at the fragments of the fragments. Okay, we'll let it go at that. This is one, as I was just mentioning to you, aroma release in the mouth is an application. We have a couple applications coming up. Aroma identification unknowns. So these are some applications. Aroma release in the mouth is ours. Identification of known compounds, assurance of purity, quantification, adulteration. Adulteration is something that shouldn't be there. Somebody's taken maybe one expensive ingredient out and put a different ingredient in. How do we know they took one out and put something else in? Mass spectrometry is the way to identify things. Oh, that shouldn't be there. Then this something else should be. This was a fun one for us. We were looking at the difference between a sugar-sweetened beverage and a non-sugar sweetened beverage. So sucrose versus aspartame, for example. And we're just interested, they taste different. I don't know about you, but I like diet beverages. I like Diet Coke as an example. It has a different flavor than sugar-sweetened Coke. Even if you use the same flavor system, it's different. And so why is this different? Why is it perceived differently? And so this was a study where we used no sweetener, aspartame, and sucrose. So we made 3 Coke-type beverages. And we, again, diluted them out, and we end up having a person, well, this happens to be orange juice. So this is the person sitting here. He's sipping on a beverage, comes into his mouth. He swallows the beverage, fellow in the United Kingdom. So he swallows the beverage, and you'll notice every time you swallow, you exhale. You always exhale, there's some exhale breath. And so he exhales, and the machine sucks that into the instrument and analyzes what stimuli was his receptors given. We know exactly what stimuli they were given because we have a mass spectrometer that's measuring it. And so it's kind of fun because you can then monitor different masses to monitor different flavor compounds. This is monitoring one flavor compound, different one, different one, different one, and so on. This is breathing. He's breathing out, so it's measuring something. Breathing in, measuring nothing because you're sucking in. And so they're measuring acetone in your breath, so we can monitor breathing. This is what we call a swallow breath. At that point, that's the highest dose that your receptors are given. And so this compound, all of these compounds were given off to some extent. But some lasted almost no time. By the second or third breath, they were gone. Some compounds got stronger as as it sat in your mouth and you processed this longer and longer. We've never had a tool like this before. We've never had a tool to measure this kind of, or get this kind of data to understand perception, human perception, how it changes before. Again, this is what we've said. How do you know a peak is what it is? Yep, we do mass spectrometry. That was a quick slide, wasn't it? So we go back to adulteration, pesticides, contaminants, odorants. There's just all kinds of different areas. Pyrolysis mass spectrometry. Do we really want to do plating? Do we want to find other ways of determining microorganisms? Which one? Again, mass spectrometry has been used for this purpose. You actually do a pyrolysis of the microorganism. So you actually put your sample of microorganism into a particular vessel. That vessel heats to something like anywhere from 358 to 770 degrees centigrade in 0.5 seconds. That's not too bad. It's pretty rapid heating. And that, of course, decomposes the sample, and then the sample ends up going into a mass spectrometer. And so you can then look at the fragments of the mass spectrometer and you can identify the microorganisms. You get a very complex spectrum. Here's a spectrum for Staph aureus. Here's a spectrum for E. coli. So again, you can do MS. I don't know if you did that in microlab. Did you give that a try? We're going to have to talk to the instructor, aren't we? We'll tie the courses together. So it's rather interesting. This is one also. You can do imaging by mass spectrometry. I'm absolutely fascinated by the creativity of scientists and where they find challenges. So take someone's brain. We'll take a mouse brain, something's better. Do a little cross section. And then you can go ahead and take a spectrum in different places across the brain. And that will give you what's there, kind of chemically, what's there, different places of the brain. And so you can get an image, a mass spectral image of the brain. What I've drawn over here is something we have going on today, and it was one of my topics talking to a researcher down south here. We're looking at emulsions. We make emulsions in the food business very commonly. And emulsions really require that our particles have some kind of emulsifier, some kind of a coating that makes them more water tolerant, can exist in a water environment. Like we take vegetable oil. Vegetable oil and water, mix them, they're going to separate immediately. But if you put some kind of an interface, some kind of a coating around each droplet of oil and make them small, they behave more like water. They'll tend to stay separated. And so the question is, what really goes to that interface between the oil and the water? If we have a simple emulsifier, it's easy. It's the one we put in, right? We put in tween 80. What's tween 80 on the surface? But supposing we take something from dairy, a dairy byproduct, something that works for us. Well, then what from that dairy product or what from a gum goes to the surface? Well, it's really not easy to know that. It's hard to measure in a liquid solution what happens to be on this 1 micron droplet. And so what we were doing is we spray dried it. So we got a nice dry emulsion. So there's enough solid material in here that we get a dry particle, and we'll have droplets of oil throughout. We break a particle in half so we can break some of these droplets in half. And this was an oil droplet, but we've evaporated the oil out of here, and then we're using a mass spectrometer to come along and keep on bombarding this and doing imaging just like I showed. And so when this was an oil droplet here, okay, we can see what was there, what's the residue, what was the interface. Really fascinating. And what makes this possible is we can resolve the composition here versus here within 20 nanometers. We have 20 nanometer resolution of this, which is just fantastic. All brought to us by creative scientists. Because a fun thing about the food business, we get to use everybody else's stuff. They come up with some good ideas. We get to put it to practice. Because we're probably not big enough in many cases that somebody will develop things for us. But if they're developing for the medical profession, they're developing for the pharmaceutical profession, they can do some really neat things. And so we keep on learning. What did they do? Oh, how do we apply it? It's really fascinating, the technology that's developed and instrumentation that's developed for us. Given 3 years ago, that didn't exist. We couldn't, get with so fine, know exactly what's there in this particle. Cost has come down. Costs come down. I'll qualify that. To run a sample here, it's $1,050 one sample because the equipment's someplace around $4 million. Okay, that's on the expensive side. But the cost has come down enough now that we can buy one, put in our laboratory. Like I say, we've got 4 of them in our lab. And so that's taken out of the hands of experts, out of people with big money, putting it into our hands and putting it into the food industry laboratories. So costs come down. It's easy to operate. Most of them are push-button systems. There is a danger, as I said. You still need to look at the data. You still need to figure out, is it what the machine said? But costs have come down. They become easy to operate. Computerized databases helps us, data handling. And so it's become really a common lab tool where at one time it was just left in the hands of a few experts. Few well-heeled experts as well. So it's really fascinating. These are some of the references. There's a good deal of literature available on the web, of course, like everything else. Amazes what you can find. If you're ever interested in LC, the web's a good place. Mass Spec organization has a lot of good YouTube videos and so on. So I encourage you to take a look at it. Do you have any questions about mass spectrometry, interfaces, the wonderful things you can do with mass spectrometry, entertain your friends, family? No? If you do, I'm in 147, by the way. Probably most of you know that. You walked by one time or another. But it is a powerful technique that we have at our fingertips these days. Okay? All you. Then I'll go away, or else I'd probably be drawing on the board and I'd be distracting people.
You can draw.
I better go.
You're leaving?
Yeah.
I sit in on your lecture.
I won't be else.
No, you can go.
Okay. Take care.
Okay. We will be giving examples about use of MS later on in the semester with other constituents that we will be analyzing. So that's not the end of MS. The MS is just beginning. This is just learning about the principle, but we will see applications. Okay, I'm going to finish up the HPLC lecture. So I was here. I don't have a recap for you at this point. But I'm assuming that since you've done the lab and we talked a lot about UV detection in the lab and last lecture, so we're good there. I'm going to move on after UV. There is another detector, so we're going to, that is based on absorption of light, but in this case, fluorescing of the light. After absorption, some compounds can fluoresce. That means emit radiation. We're going to talk about the physics of that next week when we talk about spectroscopy in general. But in fluorescence, you need also a chromophore. A chromophore, that means a compound that actually absorbs light. But in not just absorb light, these compounds can also fluoresce. So fluorescence is more sensitive than UV absorption. So you can get concentrations at lower thresholds. So it's a really powerful tool if the compounds that you're measuring actually are capable of emitting radiation. And we'll talk more about absorption and emission of radiation next week. And here are examples. It's vitamins and aflatoxins are compounds that actually absorb UV radiation, UV vis radiation, and can fluoresce. Another detector that is very common in actually the carbohydrates analysis, it can also be used for lipids, but it's a refractive index detector, and it measures the refractive index of the mobile phase and when a solute is leaving the column and when it gets to the detector, the refractive index change. So the change in the refractive index is an indication or directly correlated to the concentration. Okay? So if you have an isocratic mobile phase going through the detector, you always have a constant refractive index measurement. And then once a peak comes out or a constituent comes out, there will be a change in the refractive index. Okay, that change is what I said is related to the concentration. The higher the change in the refractive index, the higher is the concentration of that constituent. It's a not very sensitive tool, so you really have to have higher concentrations in order to be detected. So it's not as sensitive as UV and fluorescence. Now, with refractive index detection, you cannot do a gradient elution. It has to be isocratic. Why is that?
So it'll record the change when you do the gradient?
Yes, it's going to interfere with the change that you're going to deduce due to the compound. But when you're changing the gradient or when you're changing the mobile phase, you are also changing the refractive index. So if you have a compound coming out at the same time as you're changing your mobile phase, you can't detect or you can't quantitate accurately. So with refractive index detection, you always have to use isocratic elution. Another powerful detector is the electrochemical detector, which is the most recent version of it is the pulsed amperometric detector. It's more sensitive and it doesn't get not polluted, I mean, when you run a compound and it oxidizes or get reduced, the residues of it might stay in the detector and cause poisoning to the electrodes. Because in the detector you have electrodes, and what happens is you have a voltage, and when an oxidized compound or a reduced compound or a charged compound go through, it generates a current. And that current, you can measure conductivity of that. So this is how the detector works. You have a voltage applied, a current is generated based on the ions or the oxidized or reduced analyte, and then the conductivity is measured, and then the change in conductivity between the two electrodes is related to the concentration of your compound of interest. Okay, so in pulsed amperometric detector, you don't have as much of a poisoning of the electrodes, so the detector lasts longer and is more efficient and more sensitive than old versions of electrochemical detector. What it's combined with, this detector is combined with molecules that are naturally charged, so like amino acids, for example, organic acids. You can make carbohydrates charged. We can talk about that when we cover carbohydrate analysis by changing the pH. So carbohydrates, for example, they are very weak acids. So when you increase the pH a lot, alkaline, they will give you a proton. They become negatively charged, for example. We'll talk more about that when we cover carbohydrates. And then compounds like phenols, polyphenols, they can get oxidized, though you can actually measure them with this detection technique. Light scattering detector, it is really, we call it in the LC world the universal detector. Why is it universal detector? Because it can detect anything not based on any chemical composition or ability to absorb light, just the presence of the solute. So what it is, from its name, light is scattered by the solute of interest. How does that happen? So your solute or compound is leaving the column with the solvent, and the solvent and the compound hit the detector. The solvent is evaporated, and then whatever non-volatile that remains on the source of light, it will cause scattering of the light. The more the light is scattered, detector is related to higher concentration, basically. So this kind of technique can measure any non-volatile compounds. MOS is a really advanced type of light scattering detector. It's multi-angle light scattering detector. And it's commonly used with size exclusion chromatography. It has high sensitivity and high detection power. Another detector is the MS, which Curie was just talking about, which is also a very powerful tool. And next week we're going to start the MS lab coupled with HPLC. Chemical reactions, sometimes compounds don't absorb light, but you can change them so that they become compounds where you can measure absorption or fluorescence. So we call that, you can do that pre-column or post-column derivatization. That means before you inject the sample, you can derivatize it, change it to make it a chromophore, or after the column separation, there will be a unit where your sample goes in and get derivatized. Then after derivatization, it gets to the detector. So you can do that pre or post derivatization. So you can measure absorption, you can measure fluorescence. So for example here, amino acids, not all of them absorb light, only 3 of them absorb light. So the amino acids, other than the 3 that absorb light, tyrosine, phenylalanine, and tryptophan, other than these 3, you react them with a reagent, an OPA reagent, then they will produce a compound that can fluoresce, and you can measure fluorescence. Or you can react them with anhydride, and then you can measure absorption, visible light absorption. All right, this table gives you examples of different analytes. It's a good summary table. If I tell you, give me an example for a certain application of modes of separation and a detector. So here's a list of analytes. We're going to cover all of these analytes in future chapters. So we will be talking in more detail about determination of mono and oligosaccharides using cation and anion exchange, normal, reverse phase, and the different sorts of detection. When we cover the vitamins chapter, we're going to talk about separation and detection. Amino acid in the protein characterization chapter, and all of these are in a chapter we cover called chemical constituents of concerns. So we're going to, HPLC will not go away, MS will not going to go away. You're going to get real true examples of applications of these tools. So now you're learning about them, but later we're going to learn about application. But this is a good summary table. So a little bit more of examples of normal phase. So it's usually a mode of separation for relatively hydrophilic species. Carbohydrates, some pesticides, some water-soluble vitamins. Reverse phase are those for compounds that are relatively nonpolar or would potentially are able to react with nonpolar functional groups. So proteins or peptides, amino acids, some pesticides, and a whole list of them. Alkaloids is the example we had in the lab, such as caffeine. Iron pair reversed phase is also a common technique. With iron pair, if you have compounds like peptides, for example, and you want to separate them by reverse phase, some of these peptides can carry charge, so you can add an ion to actually pair with the charge of the protein so that you have a better interaction with the column. So basically you're blocking the charge. So you can block the charge so that the molecule or component can become more hydrophobic or less polar so that they can be separated by reverse phase. This is not going to dwell much on that. This is just an example separation using reverse phase versus normal phase. Not much to talk about here, but ion exchange is those compounds that you can have a charge or make them, force them to have a charge, like carbohydrates, sugars, and mono and disaccharides. You can actually force a charge. inorganic anions and cations, organic acids, amines, phenols, surfactants, etc. You can have charge and separate based on charge. Size exclusion chromatography is not highly applicable in high performance, and very low percentage of the time is used as high performance liquid chromatography. We use it in the lab for gluten proteins. We use size exclusion chromatography in the form of HPLC to separate gluten protein based on their size. But it's commonly used for larger molecules, and it's mostly for separation using low pressure liquid chromatography, where big fractions are isolated for different purposes. Affinity, we have it's mainly used really for allergens and enzymes. It can be used for mycotoxins, and glycoproteins is a very good mode of separation for glycoproteins. So this is just another example for separating of anions in coffee using ion exchange. And size exclusion, this is cell wall pactin material that is being separated by size exclusion. And this is potentially a low pressure size exclusion. And you can see with low pressure, you don't really have excellent separation. You have broad peaks and not sharp with low pressure liquid chromatography, unlike high pressure liquid chromatography. I should have shown one example from Alex's work next year. Okay, so what I want to spend the last 7 minutes or so is on this exercise here. This is related to the work that you're going to do with the LC-MS. So next week and the week after, what you're going to do is you're going to extract isoflavones from soy. And there are several isoflavones in soy, up to 12. Here we're showing 11 because we had just 11 standards of them. So in order to separate them, we ran them on a column, and then you need to tell me what kind of column in a minute. We ran them on a column and we used gradient elution. So we started at 0 time, we started with 17% acetonitrile, which is an organic solvent. So 17% acetonitrile, 83% water. And then within 25 minutes, we increased the acetonitrile concentration to 25%, left it constant for 5 minutes, then increased it again to 30%, left it constant, and then went back to 17 and did the equilibration of the column in the system at 17% for a few additional minutes. From this gradient now, is this normal phase or reverse phase chromatography? This is a very common exam question. By looking at a chromatogram and looking at a gradient and telling me whether it's normal phase or reverse phase. Hold on, I know you know. Yes, Ali.
Reverse phase?
It's reverse phase. How did you deduce that it was reverse phase? Can you explain to the class?
Because the mobile phase is polar with acetonitrile, and increasing the concentration makes it more polar.
Makes it more?
Non-polar?
Yeah. Yeah.
Okay, like the stationary phase.
Yes.
Indicates reverse.
Yes, exactly. So what Ali said is we started with mostly polar mobile phase. 17% to 83% water, that is mostly polar. You have more water. As the time went by, we're increasing more acetonitrile, which is the organic solvent. So we're making the mobile phase less polar, more similar to our stationary phase. Then in this case, it's reverse phase, where stationary phase is less polar, mobile phase is more polar, and increasing the strength in this case is increasing the concentration of acetonitrile. Good. Which isoflavone is the most polar? Which one? The first one or the last one is most polar?
The first one?
The first one, yes, because remember in chromatography we are separating based on the affinity or interaction to your stationary phase. So if something comes out really fast, that means it interacted the least with your stationary phase. So your stationary phase is more or less polar than your mobile phase. So the diazine, this first one, would want to go out with the more polar solvent. So it will interact the least. So this is your most polar compound. How would you change the mobile phase so that genistein, which is the least polar, the one at the last, would elute sooner without changing the relative positions of the other compounds? Okay. Let me restate. We don't want to change where these are coming out because some of them are really close to each other. We don't want to mess up with resolution. But there is about 15 minutes or so between this one and this one. If we want to make this one come out sooner so that my run is shorter, what can I do to my gradient? Yes, Nathan?
Instead of increasing the acetonitrile as it goes on, you could pause it maybe after like the 35-minute mark.
Well, if you pause it, this will take longer time to come out.
Okay. Oh, increase it. Yeah, so like you would up the acetonitrile.
Exactly. So you, after 35 minutes or so, after this one comes out, so here around 30%, instead of keeping it plateau, you can increase it to 40%, for example. Then this one is going to come out sooner because now the mobile phase is more favorable for that less polar compound. So then I can probably bring it up to 40 minutes or whatever. So after the last one here comes out, I can increase my concentration of acetonitrile a little bit beyond 30%. I will encourage this compound to come out sooner. All right. What would happen if you keep an isocratic elution mode at 17%? So if you don't do gradient elution and you kept it at 17% acetonitrile from beginning to end, what do you think happens? Yes, Sam?
Well, would they all be in like the same relative position, just like more spread out, like it would take longer?
Takes longer. So they are in the same relative position to each other, but then what's happening, we are delaying them coming out. And more so, this is very important, more so these that are close to each other, the peak might broaden because it's taking a long time, so it's spreading longitudinally. So it might broaden and these become big wide peak. So we lose resolution. So not only we push time, and analysis time would be really long, those peaks that are sharply separated might broaden and no longer separate very well from each other. What would happen if you keep an isocratic elution at 30% acetonitrile? What happens if we start from the beginning at 30% acetonitrile? You have good participation. Think about it. Okay.
Does it have terrible resolution because everything would just come out super fast?
Yes, I have terrible resolution. I will lose the resolution between these two and these three and these three and these three. And everything is going to just be right here at the beginning and I lose my resolution. Everybody's coming out fast because all of them like the acetonitrile more than they like the mobile phase. More than they like water, I meant to say. Okay, good. So, yeah.
So how do you know what concentration to use so that, because you're kind of like dancing a fine line between having like these like really thin peaks like super close and then having them too wide where they're all like, together.
Let me tell you, I spent a whole year on this. As a postdoc at Purdue, I spent a long time, really, literally a year trying to get good separation. Because it's just experimentation is what you take. And then you try different things, trial and error with your method until you get the best resolution. A lot of experimentation is really trial and error, especially analytical experimentation. Yeah.
Would
Would you have to do that for a single type of food or drink that has more than 11? Like how, you said you were in your post-grad Purdue for a year. Like how long would something, a food or drink that has more than 11 isoflavones take?
I don't know how long it would take. You have to just go ahead and do it. But the more compounds you have, the more challenging it's going to be to achieve resolution and get good quantification. The more compounds, the more challenge. And more fun is your experiment. I mean it, at least for me. Okay, so one quick minute, because I don't want to come back to HPLC. What I want to say here is in HPLC you can do something called tandem HPLC. So you can separate, in this example, peptides, bioactive peptides, you can separate them using different modes of separation until you get a purified peptide at the end. So basically, why I say peptides, because some peptides have the same charge, some have the same molecular size, and some might have the same polarity. In order to separate them, when you have a mixture, to Zach's point, when you have a mixture of a lot of compounds and you cannot separate them with one HPLC mode of separation, then you start with any mode of separation and you add another level. So in this example, you start with ultrafiltration. That means you separate based on size. Say less than 3 kilodalton, I'm going to gather all the peptides that are less than 3 kilodalton and take them into size exclusion. So I separate them based on their size, and I look at the fraction that has the highest activity and take that fraction that might contain still multiple peptides of the same size, and I do ion exchange chromatography. And again, I separate them based on ion exchange chromatography, look at the highest peak, which is highest bioactivity of the fraction, and then take it another and do reverse phase chromatography, and then do sequencing with LC-MS. So you can do multi-layer and separate them, and that's kind of partial to Zach's question, is when you have really complex mixture, then you have to do several levels of separation. All right, I'll end here. Oh, I lied. Hold on a second. Sorry, 1 second. Please make note of next week's lab as a group. If you are group A and B, you are doing LC-MS, ENF also LC-MS. Group C and D are doing atomic absorption for mineral quantification. I will send an email out with more detail, but please select a group leader today before you leave, so that group leader is ready to lead you in lab next week.